This is the one equation you need to know to describe a system that's going around in circles at a constant speed. It says that the force acting on your system is equal to the mass of your system times its speed squared divided by the radius of whatever circle it's traveling in. And the direction of the force is in the minus r hat direction. So if r points from the center of your circle to your object, then the force is going to point inwards toward the center of the circle. Now, the most important distinction to make here is that this isn't some new force. This isn't a new law of physics. Instead, it's a mathematical fact about the net force acting on your object. So if you have gravitational forces, if you have normal forces and friction and electric forces all acting on your system, but the net result is that it's moving in circles at a constant speed, then when you sum all of those force vectors up, you will get exactly mv squared over r in the minus r hat direction, no exceptions. So let me start by showing you why this is actually true. It's a really cool derivation. Let's start by describing the system with polar coordinates. So we already know it's traveling in a circle with radius r, so let's go ahead and define this angle here, theta, relative to some axis. So when we write down the velocity vector of our system, v vector, that's just going to be the magnitude, or speed, v, multiplied by a direction. And a nice little shorthand for the direction of our velocity vector is theta hat, which means in the direction of theta. So in this diagram over here, theta goes up in this direction, and so theta hat refers to the extension of that angle perpendicular to the radius. So theta hat would point in this direction. And as our object keeps moving around the circle, the direction theta hat keeps changing with it. So this is a nice little shorthand to summarize the fact that our object is always moving with a velocity vector tangent to the circle. But we can be a little bit more explicit about this, right? We can rewrite theta hat as a vector with xy coordinates. So if we call this horizontal axis the x-axis, and y is just the typical axis defined perpendicular to it upwards, then you can check for yourself at any angle the theta hat direction actually points in minus sine theta, comma cosine theta. So if we do a couple of quick examples, when theta is 0, this theta hat direction should point straight up, and indeed, sine of 0 is 0, and cosine of 0 is 1, so it points in the 0, 1 direction. As we go to theta equals pi over 2, and the particle is all the way up here, we would expect our velocity to point left, or in the negative x direction. And that's exactly what this tells us, right? Because minus sine of pi over 2 is minus 1, and cosine of pi over 2 is 0, so theta hat points in the minus 1, 0 direction, or minus x. So what we've written down is a mathematical fact that tells us the velocity vector of an object moving in a circular path. Any object, any circular path. So if we want to find the acceleration of our object, all we have to do is take the time derivative of this velocity. And we can write down dv dt equals a constant speed, because we're assuming this is uniform circular motion where the speed doesn't change. And we just have to multiply that by the derivative of our theta hat vector. And so we can start writing out the derivative of minus sine theta with respect to time. Using the chain rule, we can first differentiate with respect to theta, and then take d theta dt, right? So if we differentiate with respect to theta, we just get minus cosine theta, and then we multiply by d theta dt. And in the y component, the derivative of cosine theta is minus sine theta. And the chain rule again tells us we have to multiply by d theta dt. So if we factor some of this stuff out, what we're left with is the acceleration, which is the same as dv dt, is equal to v times d theta dt, which we write as omega. That's the rate of change of our angle with respect to time. And then we have a minus sign with the vector cosine theta in the x direction, sine theta in the y direction. And you might recognize cosine theta sine theta as the unit vector that points in the direction of our particle, which we call r hat. So in fact, this acceleration is simply v omega in the direction of minus r hat. And there's a really neat relationship between v and omega, namely that the velocity of an object moving in a circle is equal to the radius of that circle times its angular velocity, or how many radians it covers per second. And we'll derive that in a future video on rotation, but for now you can take my word for it. So what we can do is actually rewrite this as v times v over r in the minus r hat direction. And hopefully from here you can tell that just by multiplying both sides by mass, we find that the force is equal to mv squared over r in the minus r hat direction still, just as we'd seen. So this was just plain old mathematical deduction. We assumed that the object was moving in a circle, and we assumed that it had a constant speed, and then the math told us that the force on this object is necessarily mv squared over r in the minus r hat direction. It can't be anything else. Okay, so now that you hopefully believe me when I say this equation is true, let's see how it can be really useful in systems where objects are indeed moving in circles. And in fact, there are two really common ways in which you can use this equation. The first is as a kind of shortcut to the same thing we've been doing all along, right? The name of the game when it comes to dynamics is to look at what's interacting with your system, calculate the net force on your system, use that to find its acceleration, and integrate that acceleration to find the velocity and position of your system over time. That's what we've been doing for the past several episodes now. But sometimes integrating that acceleration over time isn't necessarily straightforward, especially when acceleration isn't a function of time, but it's a function of position or something else. And so this relationship provides a really easy way to figure out your system's trajectory over time. Because if you know that it's moving in a circle already, the only thing you're missing is how fast it's moving in that circle. And this equation, f equals mv squared over r, actually just lets you solve for v, the speed of your system, as long as you can figure out what forces are acting on it. So that's the first utility of this equation. If you know the forces acting on your system, you can really quickly deduce how fast your system is traveling in a circle. Now, this second application here is actually taking this whole framework and flipping it around. You know, there are some cases where it's hard to know exactly how much force is acting on your system. Like if it's a normal force or a tension force or something else, there's not a closed form equation for straight up calculating that force. But here, if we know that your object is moving in a circle and you know its speed, you can use this relationship to deduce exactly how much force must be acting on it. So that's the second way in which this relationship becomes really useful. So let's quickly work through one example of each, and let's start with this scenario where you know how much force is acting on your system, and you just want to find how fast it's going to move in a circle. And one of the most significant applications of this is gravitational orbits. So you can think of planets orbiting around the sun, or equivalently, you can think of satellites like the moon or artificial satellites made by people orbiting around the Earth. Most gravitational orbits are approximately circular in nature, and even if they're not perfectly circular, this equation still approximately holds true, so we're still free to use it even if the orbits are technically elliptical. Anyway, when it comes to gravitational orbits, we know that the gravitational force pulling on the orbiting body is going to be gmm over r squared. So I've used a capital M to denote the mass of the central body and lowercase m to denote the mass of whatever object is orbiting it. And so the technique here is that since we know our object is going in circles around this central point with a constant speed, then we know this gravitational force has to equal mv squared over r, right? There's no way around that. And there are no other interactions, right? It's just the gravitational force that's causing this object to move in circles. So we're left with this equation, and right away, we can solve for the velocity of our orbiting planets or satellites, right? We get v squared equals gm over r. And in fact, the masses of our orbiting bodies, our satellites or our planets, cancel out of this equation. So regardless of what mass your object is, it'll orbit the central body at the same exact speed if it's placed at the same radius. Now, one cool thing you can do from here when you know the speed of your orbit is to actually compute the period of your orbit, or how much time it takes to go one full circle. And to do that, all we have to do is substitute v equals 2 pi r, the distance you travel, over t, the time it takes to travel that distance. And so we find that 2 pi r over t squared is gm over r. Or if we simplify this a little bit, carry some things to other sides, we get the famous relationship that r cubed over t squared is equal to gm over 4 pi squared. And this is actually Kepler's third law of motion, which is a really powerful statement relating the radius of a planet's orbit to the time it takes to complete that orbit, or what we call a year. So we can really quickly get a lot of information out of the forces acting on our system if we already know beforehand that we're going to move in a circle at a constant speed. But now let's look at this other application, where we know the speed with which we're traveling in a circle, and we want to figure out how strong is the force responsible for that motion. And the example that I came up with for this one is actually a pretty cool party trick. Or at least I think it's cool. And I think it's cool because anyone can do this, but only a physicist can really do it safely and knowing that it won't go wrong. So here's the setup. You have a rod. I don't know, maybe you can call it a selfie stick or what have you. And at the end of the rod, you can put a square of Velcro on it. And using the Velcro, the physicist attaches his phone to this selfie stick. And I don't want these videos to get outdated or anything like that, so let's go ahead and call this the iPhone 20 Pro Max Super Duper whatever other adjectives Apple can throw on there, okay? So this is some massively expensive iPhone that you totally don't want to fall off the Velcro. But nevertheless, you're doing this party trick, and what you do is you take the selfie stick and you spin it around in circles with some angular velocity omega. So again, this variable tells you how many radians per second are covered by the spinning motion. Or if you like, it's the number of cycles per second times 2 pi. And of course, we know the length of this selfie stick, let's call it r, so we can figure out the velocity of the phone like we did before, right? V is simply equal to r omega. And so now you see how we start out knowing v, because if the physicist can spin his selfie stick at a certain angular frequency omega, he knows how fast the phone will be moving to begin with. Now what he doesn't know is the force that the Velcro exerts on his phone throughout this motion, right? That's not something that's particularly easy to calculate. But what the physicist knows is that if you add up all of the forces acting on this phone, which in this case is going to be some Velcro force, F sub v, and some gravitational force, F sub g, right? Then if you add up those force vectors, what you have to end up with is mv squared over r in the minus r hat direction. Now, when the phone is at the top of the circle, so the system looks like this, both the Velcro adhesion and the gravitational force are pulling down on the phone toward the center of the circle, which means that their magnitudes, Fv plus Fg, have to add up to mv squared over r. That equation's pretty simple. But when the phone is at the bottom of the circle, like this, now the Velcro force is pulling up, but the gravitational force is still pulling down, which means that even though the Velcro force is pulling in the minus r hat direction, the gravitational force is pulling in the plus r hat direction. And so when we add them up, we get this relative minus sign, and we end up with the Velcro force minus the gravitational force has to equal mv squared over r, assuming all of these are in the minus r hat direction. And what that means is that the value of this Velcro force is subject to change over time, and in fact, the Velcro force is going to have to be higher at the bottom of the circle in order to compensate for the fact that the gravitational force is pulling the phone away from the center. And so it's at the bottom part of this trajectory where the Velcro force is actually maximized. And if the physicist is worried about his phone flying off of the Velcro, then this is actually where he has to be most worried, because here the necessary Velcro force could be higher than what the Velcro is physically capable of providing. And in fact, you can solve for how strong that force has to be, right? You can solve for Fv is equal to mg, which is the gravitational force, plus mv squared over r. And all of these quantities on the right-hand side are known. So what the physicist can do in order to do this party trick safely is actually calculate that number, figure out what mg plus mv squared over r is, and see if he can just pull the phone off of the Velcro using that much force. And if he can't, that means that even when the Velcro force is highest, the phone will still remain attached to it. On the other hand, if that much force is enough to pull the phone off the Velcro, the physicist is going to have to spin his phone with a smaller velocity or a larger radius in order to reduce that required force until it's no longer sufficient to separate the phone from the Velcro. Okay, so moral of the story here, don't let anyone tell you that physicists don't have any cool party tricks up their sleeve. Okay, so by this point, some of you might be skeptical that there are only so many situations in which things moving in circles actually maintain a constant speed. And you're right, in the real world, there are plenty of systems that undergo circular motion, but whose speed changes over the course of that trajectory. Luckily, though, there's actually a lot that we can say about those situations as well. And so this is what we call non-uniform circular motion, or circular motion that has a non-uniform velocity over the course of the trajectory. And here we have a bit of an example here where a ball is sent rolling up a circular track, and as you might imagine, by the time it gets to the top of this track, it's lost some speed because it's gained potential energy, right? Gravitational potential energy, as we talked about in the last episode. So this is a very archetypical example of the ball trying to go around in a circle, but not at a constant speed. So let's see how much we can still say about systems like this, where we can't really assume that the speed is constant over time. We can still start with our original equation. The velocity vector is equal to the speed at that moment times theta hat at that moment, right? All this equation says is that the velocity is tangent to the circular path. But when we want to find the acceleration, when we want to find the derivative of this velocity vector, we have to use the product rule, right? Now we have to take dv dt in theta hat and add v times d theta hat dt. Now we get two terms in this derivative. Now what you'll notice is that this term is exactly the same thing we had before, right? This is exactly what's going to give us v squared over r in the minus r hat direction. And we call this component of the acceleration the centripetal acceleration because it points toward the center of the circle. So it's center seeking, or in Greek, centripetal. And as you might have guessed, if we multiply this equation by r and we recover our mv squared over r in the minus r hat direction, this is simply called the centripetal force, or the component of the total force acting toward the center of the circle. On the other hand, now that our velocity is changing, that's not all we get. We also get this additional term, which measures how fast the actual speed of our object is changing over time. And it still points in the theta hat direction, right? This is just some number times theta hat, so it points tangentially to the circle, not centripetally. And so we call it the tangential acceleration, a tan, right? And that's going to be some number, maybe I'll just call it a tan without a vector, in the theta hat direction. And as before, if you really want, you can multiply both sides by mass, and you'll end up with the tangential force, F tan, equaling m times a tan theta hat. And just to remind you, a tan is what I'm calling dv dt. So how do we interpret this result? Well, one aspect of it is pretty straightforward and pretty similar to the case of uniform circular motion. When we had speed being constant across the whole trajectory, I said that if you add up all of the force vectors, you're going to get mv squared over r in the minus r hat direction. But now there are two things going on simultaneously. The first is that if you sum up all of the components of the forces acting in minus r hat, then you'll still get mv squared over r. But if instead you sum up all of the components of the forces that point tangentially, or in theta hat, then you'll just get m dv dt. So we still have some powerful tools at our disposal, right? If we want to know the velocity at any given point in this trajectory, we just add up all of the radial or centripetal components of the forces. On the other hand, if we want to know how our speed is changing over time, we have to add up all of the tangential components of our forces. So let's practice these ideas by thinking about this setup on the right, where a ball is thrown up a track, right? And let's say it starts off with some initial velocity, vi, and it ends up on the top with some final velocity, vf, which is less than vi because it loses kinetic energy as it gains potential energy. So let's assume that vi is high enough to get it to the top without rolling back down. But at this point, there are still two different trajectories that the ball can take, right? One is we can imagine it continuing to move along the circle, but the other is if it's slowed down sufficiently, we might imagine it actually just falls down. So how can we figure out which one is going to happen here? Well, there's something that we know has to be true in order for it to continue moving in a circle, right? And that's this equation over here, which I'm going to move to the top. The sum of the forces acting centripetally has to equal mv squared over r. And I'll just write vf here to be consistent. So at the top of this trajectory, what forces are acting on the ball? Well, we have gravity, right? Of course, we have mg in the minus r hat direction. And we also have some normal force, n, coming from the track itself. And the sum of those two has to equal mvf squared over r. So the point here, the conceptual idea, is that if this equation can hold true for some normal force, then the ball will move in a circle. But if this equation can't possibly hold true, then the ball can't possibly move in a circle. And so what do I mean by whether or not this equation is possible or impossible? Well, for that we have to recognize that this normal force is greater than or equal to 0, because you can't have a normal force pull the ball upwards, which would correspond to negative force in the centripetal direction, right? So what that means, because n is greater than or equal to 0, we get that mvf squared over r has to be greater than or equal to mg. Or if you solve for vf, you get vf squared has to be greater than or equal to gr. If that condition is met, if the ball makes it to the top of this track with a higher squared velocity than gr, then it'll continue its circular path, because indeed the force will be equal to mv squared over r. But if its velocity is lower than gr, then there's no possible way to make the force acting on this ball equal to mv squared over r, and the only alternative that the ball can take is simply to fall. So there you go, this centripetal force equation holds true and remains very powerful even if the velocity of our object changes as it's going along its circular path. Now, the last thing I wanted to mention is actually an important point about orbits. So let's imagine that we have some sort of central mass over here and some planet or satellite that's orbiting it in a circle with velocity v. So what do you think is going to happen to this orbit if something bumps into our planet or satellite, even just a little bit? Well, if there's any impulse to that planet or satellite, then its velocity is going to change, right? Its velocity will become some new velocity, v prime. And we know that the gravitational force on this object, Fg equals gmm over r squared, was equal to mv squared over r, because it used to be moving in a circle, but now that can't possibly equal mv prime squared over r, because v prime is something different from v. And so what that means is that if this planet's velocity is changed even just a little bit, it can't possibly move in a perfect circle anymore, because the force acting on it doesn't change, but its velocity does. So what ends up happening is that this object, instead of moving in a circle with velocity v, is now going to have some velocity v prime and move in an ellipse. And of course I've exaggerated here because maybe v prime isn't very different from v, but the point is that the trajectory can no longer be a perfect circle. Now, one thing that you could object is you could say, well, sure, the centripetal force doesn't change and the velocity does, but what if the radius also changes, right? What if you can write Fg equals mv prime squared over some new r prime? In other words, if the velocity of this planet increases, what if it just moves in a circle but at a higher radius? So something like this. And in principle, it's true that you could equate the gravitational force to motion at its new velocity with that radius, but the problem is that the point that it starts at, right, this initial point right here, where the collision took place and changed its velocity from v to v prime, that's not part of this outer circle, right? So it can't be moving along this perfectly circular trajectory if its initial position isn't on that circle. So that's not a physical possibility, and indeed the only thing that can really happen is it'll start moving in an ellipse through that same initial position. Or technically it can move in a hyperbola, but we'll save that for another story. And this is actually where I'm going to end it here. I'm going to keep it a nice short episode about circular motion and centripetal forces. And as always, if you guys have any questions, feel free to ask them in the comments below. And also let me know, do you like the episodes to be short and succinct like this, or do you prefer the longer ones? I'd love to hear from you, and I'll see you in the next one.